Okay, good morning, everyone. Welcome to our physical chemistry lecture. Yesterday we finished the subchapter 6 on, still have this open here, on the measurements and superposition. Okay, so we did this chapter yesterday, and today I'd like to discuss the position and afterwards the postulates of quantum mechanics. The postulates is just a list that's going to be rather quick, so maybe today, but latest early next week we will be done with this subsection, with this chapter here, this second chapter of the entire course, and we will proceed to the variation method after that. Okay, so the variation method is much more applied, and whatever follows in the course will be more applied and more specific. It's really the second chapter, which is fairly abstract, and where you need to hold on and try to appreciate the aesthetics of the underlying framework, right? That underpins all the physics as it is manifested in chemistry. I'd still like to make one final remark. Yesterday I was a little bit sloppy when we discussed these wave functions, and what I wanted to say is this, right? So in this last example of the particle of the box, we presume that we know a wave function, right? It doesn't even matter if it's the true wave function, right? But we just presume we presume that this is the true wave function here. So that psi is proportional to this x times brackets L minus x. And it's important to first look at what that means. So if you set your x equals L, right? So I did a little drawing here. So if your x is here for L, right, and you substitute it, then in your bracket you have L minus L, and that means that your psi is going to be 0, right? So for x equals L, your psi is 0. Now, does that make sense? It does, because at this L, your potential is supposed to go to infinity. Okay, so there should be no wave function, right? If your potential is infinitesimally repulsive, the wave function must collapse, right? Now, this is, if you wish, so we always say, well, things can tunnel through and so on. Wrong. It depends on your potential. If your potential is infinite, nothing is going to tunnel, right? So we have to be clear on that. So it's going to be 0 at v for x equals L, right? It's going to be to infinity, and anything afterwards is going to be 0 too, right? So that's the realm. It's inaccessible for your electrons, right? Okay, what happens for x equals 0? Well, that's easy. So x equals 0, then you have 0 times some bracket, and that means psi equals 0. Right? So also for x equals 0, we are here, right? Now what happens in between, right? So 0 smaller equals x smaller equals L. Well, we can simply multiply this out, right? In that case, psi is proportional to minus x squared plus Lx and that's it. So this means you have something quadratic. The leading order is quadratic for your wave function, right? Should look something like this. This is sort of the truth, right? And now we discussed expanding this wave function. So think about it as an approximation, expanding this thing in your Eigen Functions, right? And the Eigen Functions of the particle in the box, you know, it's always this sinusoidal functions here. We discussed them yesterday, right? It's these guys, okay? So we call them Gn. So we expand this in Gn. Or I, doesn't matter. And the first one, we know the first one is gonna be 1, so half a period of a sinus function. And that's probably gonna look something like this, right? And now you see, that's your first approximation, right? And you see the difference, there's a remaining difference. Now, if that difference was 0, if delta psi, so if the difference between psi and G1, 0, then your C1 squared, which is the probability, must be equals 1, which means that you fully recover exactly the wave function with this one eigenfunction, right? So it has perfect overlap. And then according to our discussion up here, right, for our probabilities, right, that would be basically, in this case, this probability would be 1. And then you have identity of this one eigenfunction for that total wave function. But that's not the case, as you can see here, right? The half a sinus period is not the same as a quadratic function in the same boundary, and so there's a difference, right? And this difference manifests itself in this difference between the coefficients squared, right? So here you see in this probability, you see how much the second, now in this case the third one, because the even eigenfunctions don't contribute, but the third eigenfunction, how much will it fill up? And you can see that here, right? It's exactly these guys here, this part and this part, that will be covered by your third eigenfunction, okay? So you see here is a little bit coming, right? That part will correct this, and that part will correct this, and this part will help up here, right? And these parts, right? And they will help with the C3 squared amount, right? So this is a conditional thing, right? If that was true, this is not the case, right? So let me phrase this correctly. But not the case here. C1 squared is smaller one, okay? You're missing roughly between 1 promille and 1%. So next correction. From G3 and C3. And then the one after that, subsequent, you become increasingly more accurate in approaching that true wave function you will get G5 and C5 squared. And then we discussed, right, the C7 already escapes the precision, the number of digits we had available in our little table, right? So after that, right, after 5, you presume that the eigenfunctions you used in this expansion model the true wave function sufficiently well for all intents and purposes. Okay, so it's a convergence question. What are these intents and purposes? It depends. Maybe if you do a thermochemical experiment, G3 is enough, right? If you go highly spectroscopic, highly accurate, maybe you need G9, right, to still get that last digit so that your prediction matches the experiment. So with this, you see the power, the versatility of these eigenfunctions, but you also see the limitations. Okay. Are there any questions left for this? Doesn't seem to be the case. So let's proceed with the next subsection. And that will be, so we're in chapter 2, and now we're going to discuss 7, the eigenfunctions of the position. Now, if you think about this title, right, you should immediately by now wonder what does position really mean if you have a wave? Right? Imagine you go in a swimming pool and you create a big wave, and somebody asks you about the position of the wave. You're going to say it's all over the swimming pool, right? It's inside the pool, obviously, but which position, right? It's anywhere in the pool there's going to be the wave, right? And so that's what we are doing for our electrons, right? We mentioned the double slit experiment yesterday again. It's a wave function, right? Which electron is going to be where? I mean, so electrons are indistinguishable anyways, right? So what does it mean really, a position? And you see, there's something ill-defined. It's something contradictory with the entire framework. Yet, of course, we need to ask this question, right? This is, the position is a key variable in all of mechanics. And so we need to explore this, right? And so this is why this deserves an entire subchapter, because it's eminently an important quantity. Now, what is the position? The position, so position X, we are in quantum mechanics, so now we call this an operator. And formally we do this simply by putting a hat on top of it. Okay. So because we did this, right, you're implying all sorts of things. We already said all quantum operators are heroes, so let's stick with that. But it's not necessarily so that this operator is as multiplicative as the classical position, right? We haven't shown this yet, so we cannot assume this. Maybe there's some weird quantum thing which is extremely non-local, and so you cannot presume that this is multiplicative. All right, so let's use this operator, right? So in this case we know the eigenvalue, right? The eigenvalue should be the x, the position, right? That's what we know. And we're going to sort of reverse engineer the operator and the eigenfunctions, right? So we know and the logic is quite similar to the parity discussion, right? We know certain things, and based on that we try to figure out more, right? So we know that when x operates on the eigenfunction, right, we should get the position back, right? And that position of the eighth eigenfunction can be eigenvalue A of that eigenfunction, right? So let's call that XA. Okay, so we define it that way if you wish. Okay, so we define our X to be this value A, right? The value A is gonna be what you measure, right? In your single experiment. Now, A is an eigenvalue, so it's a number, right? And your X position from your operator, that's also a number, right? So these guys, so this guy, we don't know if multiplicative. At least not a priori. But simply a variable X or a number A is certainly multiplicative. So good news. By the simple definition, we now can assume multiplicity, that things are multiplicative. And so we can, for this reason, from this definition, we can see that X minus A, so we can pull the AG on the left-hand side and then X minus A, and then we factor out GA must be 0, okay? So now you have a product of two things, right? Once you have this bracket and once you have this eigenfunction. And this product must be 0. Now, there's only 2 cases now, how this can generally be true. Generally. So this is generally true if and only if either your X equals A and your GA non-zero, right? X equals A, then your bracket is 0, of course, or if this eigenfunction is 0 for all A's that are not equals X. These are the 2 cases. Right? In other words, your eigenvalue A must be the position X. Okay. So 2 consequences, or 2 conclusions, rather. This latter case is the trivial solution, which is without interest. Your eigenfunction is 0, it means nothing is there, right? Mathematically, it holds. And so whenever you go to this case where your eigenfunction is 0, right? Clearly your eigenvalue then is not that position, right? So you cannot really get anything. The other important thing is that we learn something about the eigenfunction, right? So the eigenfunction is 0 except when x happens to be equals a. Right. So if you scan axis, right, you should only see something at x equals a. Now, what could this function be? Which function does this? It basically switches off everything except when your variable equals some constant or some value. Right? Which mathematical does that job, if you wish? It's a bit colloquial, but that's basically what we are looking for. Now, it's not obvious, right? Most of you will probably not know this. So I'm going to give you the answer to that, right? But that, of course, does not reflect all the time that went into people trying and finding this function, right? So it's the training and experience which makes it then obvious that for such cases you use the following. And a good way to see this is to consider first the Heavyside step function. So step function, by the meaning of its wording, means that there's going to be a step, which means it's not differentiable, okay, or there's something discontinuous, something nasty is happening, okay. Now this function is well known. It typically has the symbol h, and it contains an argument x minus a, and it's defined such that it is 1 for all x larger a. It is 0 for all x smaller a, and it is 1/2 for all x equals a. Okay, or if x, let's put it like this, if x equals a. Okay, so that's easy to plot. So here you have h 0, 1/2, 1. This is x, and this is a, right? And when x equals a, the function must go through 1/2. At x equals larger a, it equals 1, and at x equals smaller a, it's 0. Right? So this is the step function, right? It gets you from 0 to 1 as soon as x passes a. There are other step functions, but this is quite a common one. Now we do something which is weird. We're going to ask what is the derivative of this. So what happens if we differentiate? Okay. Well, so we write down our differential operator applied to x, and this derivative gives you something which is known as the delta function. This is basically defined. This is the Dirac, also known as Dirac delta function. It's actually something like the continuous variant of the Kronecker delta. Okay, if you imagine a sum running over some summons and there's a Kronecker delta in it, the Kronecker delta will switch off everybody except that term where the two indices are the same. And the Dirac delta function does something similar, and it does it in the following way. Delta of x minus a is this derivative, and it is 0 for all x non-equals a, right? So on the left-hand side and on the right-hand side of a, it's flat, right? So you have 0 gradient, so it must be 0 here. And at a, it's infinity. Okay. Now, how does that help us? It helps us in the following way. We can use partial integration, right, to see that. So, and again, we already made use of partial integration when we discussed the momentum operator and how it commutes, how it's a hero, and we'll do that here again. So two functions u and v are the integral of u, the derivative plus u prime v. Okay. So you know this, and what we're going to do now is consider this integral. We go from minus infinity to plus infinity. So in this graphic here, right, you have your h. You go from all the left, from minus infinity, all the way to the right to plus infinity. Okay. And we have some function f of x unspecified and our derivative. Right. And now we thanks to partial integration, we write this, thanks to our definition and above, we write this f on x delta x minus a. And this must be the same thanks to partial integration as our definition. We have the stem functions minus infinity plus infinity for f times h minus dx h, and now we have to derive f, right? So let's write this in more detail then. So we have f at infinity times h at infinity, h is, remember, has as arguments x and a, right? So we have infinity minus a. Now infinity minus a constant is still infinity, so this is 1, okay? And then we have minus f of minus infinity times h of minus infinity minus a, and minus infinity minus a constant is still minus infinity, so here h must be 0 per our definition above. And then we have, of course, our dx, and now we're going to do another trick. Rather than going from minus infinity, oh, let me write this out. So this is minus infinity plus infinity. So we're going to divide this integral in two integrals. Once we go from minus infinity to a, and then we go from a to plus infinity, right? So you can partition your integrals in as many parts as you wish, as long as you make sure you don't count twice and so on. So we only go up to a, right? And we integrate hx minus a up to a, and that integral is just summing up zeros, right? So this must be 0. Right? And so we are only left with the second integral from a to plus infinity dx of hx minus a, and that part is just 1. That gives us dxf, right? So basically this term dies and this term dies, and you're left with f at infinity minus your integral from a to infinity dxf, right? Now when you integrate a derivative, you simply recover the stem function, right? So this is the same as f of infinity minus f at a and infinity, and so this is the same as f infinity minus f infinity plus f at a. So your entire integral here, right, becomes f of a. So let me write this again. Dx of some function of x, doesn't matter which one, could be your wave function, with delta x minus a minus infinity to plus infinity. So over the entire range where your electrons live, right, will spit out your function at the position a. Okay. So this you can, of course, let me change the order here. X minus a times f of x. Now this really looks like a projection operator or some integral operator. Right? You have something, right? It acts on the right-hand function, and out comes your function at a particular value, right? So it's analog to the projection, and for that reason we simply do the ansatz now, right? For our position. That GA of x is nothing else than the delta function x minus a. So let's test this, right? So we follow the projection procedure, right? So consider this: we take a dA, right? So our variation in the position we are interested in. And this is some probability for the position. So we would take, in terms of a projection, we would take our corresponding eigenfunction, right? So we want the probability of that position, right? So we project now in here to the same way as in the previous chapter we discussed how we project out our probability, okay? So we project this in onto our electron wave function. Okay. Looks good. This is dA dx minus infinity plus infinity GA. We would traditionally now take the complex conjugate. Let's just do this formally, write it once more, right? And now using our ansatz, we write this as dx delta x minus a psi x t. dA, just flip the dA on the other side. And that means, right, as we have shown above, see above, this integral from minus infinity to plus infinity is nothing else than our wave function at a t squared dA. Right? So this is our probability for the position A in the spatial window of A. Right? So this expression is so we can pass the test. It's consistent with Born's rule. Okay. So remember how in the beginning of the last chapter, let me scroll up here, we still have it. We mentioned Born's rule, but we didn't derive it, right? Where is it? Oh no, this was still on the, it's up here, this here, right? But just replace here the x by the a for the specific location, right? This is a probability, also known as Born's rule. We started talking about probability for this reason, and then we derived the framework of how to do this with these probabilities. And now you see this applied, and we tested to see if for the position eigenfunctions we can recover Born's rule. Right? So we've recovered Born's rule. It's consistent. We can now assume that x delta x minus a will correspond to these kind of eigenvalue equations.
I'm sorry, I have a question.
Sure.
In the third last line, wouldn't that have to be conjugated as well?
Yeah, so this is the formal, so this is still a formal step, right? So this is generally our mechanism, right? If you just write out, this is identical, right? And in our ansatz, you insert now for GA the delta function, and this one does not have a complex conjugate.
Oh, I see. Thank you.
So you can, I mean, forget about this line, right? It's just for completeness sake. Now, the derivation we did here above was a little bit, a mathematician would object to this, right? Because it does not meet all the assumptions, right, on differentiability discussions, limit discussions, and so on and so forth. And you have to be a little bit careful with this. So watch out. These delta functions can be ill-behaved. Right. Above derivation is rather informal. So you would really need to discuss the limits, since it lacks proper consideration of the limit of some sigma going to 0, f of x equals delta, using, so typically what's done is you use some Gaussian, right, some approximate f of x with some sigma width, and you look at this. This is x, sorry, we should use x minus a squared over sigma, and then at a, you would have a Gaussian, right? And then this has a certain width, sigma width, and then you have to discuss how this changes as your sigma varies, right? And this limit discussion, right, it's formally you will have to make use of this in the derivation to show that our partial integration and all these things may hold. We didn't do that. I don't think you need this. If you're interested in this, it can be shown mathematically, but that would lead us too much astray from actual chemistry problems. So we're going to skip this. Okay, I see we reached the full hour. We have the next section is sub-chapter 8 on the postulates and quantum mechanics. This is sort of a summary, if you wish, of what you had. It's distilled in the most important statements. It becomes sort of a laundry list, right? So it will not take us long to get through this, but it's very important, of course, that you have heard about them. We will discuss them on Monday morning. I'd like to conclude today's lecture, and if there are any questions, this could be a good moment. If that's not the case, I'd like to thank you for your attention, and I wish you a good remainder of the week. Bye-bye.
Bye.